So my talk is on cheminformatics before cheminformatics. But before getting there, I'll say I am a software developer. I am not a chemist. I don't pretend to be a chemist. Self-employed, I live in Sweden in Trollhättan, which is once upon a time when trolls were happy things, not network things. Saab had made cars here, and we had stickers on the windows that said made in Trollhättan by trolls. So I software developer, started off in structural biology, did some bioinformatics, and then have done cheminformatics since the time the cup was made. And I've also been doing Python as my primary language since then. So I decided to give the talk on cheminformatics before cheminformatics. Of course, what is cheminformatics and when is it? You go to the paper by Frank Brown and look it up, and it says chemoinformatics is chemoinformatics. Oh yeah, there was this discussion about is it cheminformatics or chemoinformatics? We'll just call it, I'm going to call it cheminformatics. I think it's pretty much everyone's agreed from it. And it's a very 1990s paper about what they're doing in their group. And I mean, you can look at the artwork there, the figure of the person on the computer. That's 1990s clip art. And I don't think it's that useful in terms of characterizing what cheminformatics is. But there's a few keywords here on the side. They'll pull out silos and 2x5 cards and other things. Now, other people responded to and filled out what is cheminformatics. And Gastiger wrote one that's pretty influential. Cheminformatics is the application of informatics methods to solve chemical problems. And which roots going back more than 40 years. In the early 60s, various forms of machine-readable chemical structure representations were explored as the basis for building databases. So here's a question. These are machines, right? These are punch card machines. Computers are machines, sure, but these are machines too. So what about punch card machines? Oh, sharing is paused.
It looks like your slides aren't advancing.
Okay. Pausing is shared. Bring your shared window to the front.
Nice.
Okay, but that's just the... So how if I do this? All right, sorry about this. Do this. Do this. Now we'll just do this old school style. You get to see everything. Share screen. All right, you get to see outline stuff too. So there's punch card machines. These are machines too. And these machines, well, I'm just old enough that when I was a Cub Scout, we went to the local bank, and in the basement, we got to see the punch card machines that they had in the bank. But by the time I got to college, the guy who was maintaining the punch card machines had retired, and they didn't have any more machines anymore. So punch cards started off effectively for the US for business purposes in 1890 with the census. The problem is there we're having so much analysis to do that they expected to take more than 10 years to do a census, which is going to be a problem. So Hollerith came in with a solution of using punch cards. You take the information, put it into the cards, stick into a machine like this, and let the machine do the sorting. These sorts of machines were, as it says there, at least 10 times faster than manual sorting. So they could do 60 million cards for the punch card census, sort them, and use these little dials over there to do the tabulation. So if those are machines, what about this? Is this a machine? I think it's a machine. It's a punch card machine. It's a classical lever right there. So let's call this a machine. This is an edge notch punch card. And what a edge notch punch card is the previous one you saw had holes in the middle. Those are interior. Edge notch has holes on the side, and you take the punch and you go clip, and you make a notch on the side. And then you take a rod, often called a needle, and you stick it through these holes and lift it up. And where the hole is, it follows along with the rod. Where the notch is, it falls out. So now you have a way to take a set of cards and separate them, sort them, use other techniques on them. Now these were first used in 1930s to start storing physical data. This is a 1936 publication, which is taking the information on the cards, sorting the cards by specific gravity, and then you can see over in the middle there's the strength. And the strength is correlated to the increase in specific gravity. So therefore, this is a new visualization technique, new analysis technique that you weren't able to do with previous systems. Now, there are many ways you can encode information on cards. The simplest one is what's called direct coding. You have 680, so you cut the notch for the hole for 6, cut a notch on the hole for 8, and cut a notch on the hole for 0. There are more complex coding like triangle codes where you take the intersection and use 2 needles to lift that. You better use of space. And that book that I referenced on the board, excellent book for manual, excellent book about information processing in the early 1960s. Now, punch cards, but Gastiger says machine readable chemical structure representation. So I showed you was saying about trees. Go back to Freer. During the Second World War, there's a letter in Science where he's saying he's collecting all materials that have been tested for insecticidal or fungicidal properties. He wants to take a catalog, looking for data, compound, other information that can go into these catalogs. And then just after the war is finished, he does a publication where he's showing one of his cards. These are the edge notch codes that I'm talking about. On the top, there are holes for the identifier 1374. On the side, there's basically a little bit that says this is an insecticide, it's not a fungicide. And then on the bottom, it's the descriptor code for the most important chemical constituent. In this case, it's ethyl alcohol, so it's just a hydroxy compounds mono. Now, and then on the side is relative toxicity, which in the paper they point out is by taking all the cards that have a certain feature, comparing that to toxicity, doing the sum of that, and figuring out what the toxicity is. And for some modifications of that, you could do correlation studies between chemical constitution and any desired property, chemical or physical. So this sounds like what we do a lot of these days. And the code that they had was pretty good. So you take here's the structure is DDT because it's an insecticide catalog. Take DDT, you'll find, okay, there's 5 chlorines. Look up the chlorine entry. That's number 855. You've got the 2 benzene rings. Look that up. That's code number 952. And then there's the 2 carbons left over, and that's entry 1011. And so you have an index sorted by the smallest number, and it gives you a way to look it up and a way to correlate. This went off pretty well. People like this. So the National Research Council started the Chemical Biological Coordination Center, established with, you can read all that at some other time. I think you all know where the slides are. I put them online, and Brian can give a link too. But the main one here is to assemble and organize information related to the effect of structure of chemicals on their biological activity. And very soon, within a year or two, they had moved to using this is the IBM card that everyone who thinks about punch cards probably almost certainly thinks of these sorts of punch cards. So you have a serial number and the 10 spots for the structural code, not just 1 spot, a place for the molecular formula, and the place to encode physical or biological properties or other data. And then the problem is okay, what's biological properties? People love this, by the way. People use this code for about the next 15 years. They'd have to modify it for their own chemical systems, but this was a very popular code. What about biological codes? So they worked on that. That took about $40 million present day, $5 million then. When he ran out in 57, people on staff, 3 people kept on going for another 3 years to make this book release. It was never used. And so you go back to Frank Brown's 1998 Cheminformatics paper, and he talks about how no one was asking or realized the value of looking at all the test results at the time. And I'm reading this book from 1960s saying, we want to do this so information of one collection can be collated with that of another, at least with public information can. And we really hope that even if it's not used now, someone in the future could build on this and use it. As far as I can tell, it wasn't. And this even describes the difficulties of, it's easy to do something that's useful for one system, but not for one that's good for every system, which is kind of, in some sense, information that it doesn't make its way through into the reason, understand why these sorts of silo systems existed and that they're even understood back in the 60s. So then I talk about this, point this out, but most people at this time were not doing these sorts of fancy correlations with punch cards and stuff. They were interested in doing chemical bibliographies. So remember, Freer's catalog started as a project started as a catalog project, not a correlation studies project. And there was this problem with this. World War II was producing so many documents, new reports coming in that couldn't be handled well under the existing systems. And you had things like the German reparations. We got something like, I think it was 750,000 chemical records from Germany that Chemical Abstract said, we can't do this. We'll hope somebody else processes it, makes it into literature, and then we'll index it. Just information overload. Well, that term wasn't around for another couple decades. So in 1945, there's this publication in CNN about using punch cards, these same sorts of edge-notch punch cards for bibliographic information. At a regional meeting, so much interest in this, a special session for it, something like 80 people showed up. The ACS started a punch card committee so they could figure out how do we do this. There are lots of publications in the Journal of Chemical Education describing how this works. But you have to think about this. This is part of what's called the documentation movement. And now when I started in this field, like, okay, documentation, that's how I do my software. I write some documents, right? This is more of a idealistic thing than that. Documentation was this project, the movement started off in the 1890s as a sort of set up a comprehensive bibliography of everything written since the invention of printing. And one of the quotes in here, a giant intellectual mechanism which aimed at collecting and condensing scattered and diffuse knowledge in order to distribute it wherever it was needed, and to provide information to people, not just documents. So when you look at what they did, one of the things they established was the 3x5 card indexing system and universal decimal classification, which is, they saw a Dewey Decimal System and said, amazing, and went on to develop that and did some other work as well. So when you see, again, going back to the Cheminformatics paper, you look in there and it says things like the best model is the way a library uses a card catalog or a form-based interface, much like the 3x5 index cards of the past. So you can see this connection between this paper that's in the late 90s to almost a century before about 3x5 card and organizing information. And the outlet went on to describe the mundanium of having a city based around making information available to anybody, send it by telegraph and get a response back with microfilm if you want it. So by bearing that in mind, you can then read some of the literature, like here's Charles Davis describing indexing and index editing at chemical abstracts before the registry system, before the 1960s effort to computerize. And you can see things like well-established techniques derived from documentation in library science. That's the same documentation. It's not the how do you handle documents physically, but the concept of this global ideal of information management. You can also see they're using 3x5 cards all over the place because that was well established. So when you see something like the Journal of Chemical Documentation, which is the original name for the Journal of Chemical Information and Modeling, that documentation means something more like information science. It does not mean, here's a document. And so that's why in the 1950s, you saw chemical documentation work, questions about how to index chemical records in the journal American Documentation. And then too many people were publishing there basically. So the specialized journal started, Journal of Chemical Documentation. Even in the 60s, it was kind of old-fashioned term, so they became JKICS in 75 and the JCIM in 2005. But this explains my confusion when I started this field of why is Sheffield in the postgraduate school of librarianship and information science? Because I didn't know that there were these deep connections between cheminformatics and library science. Now, we talk about silos. I'll mention here a bit about one other way to solve the silo machine. This is before machines. The silo problem is this question of, you've got a structure, I've got a structure, are they the same structure? So the nomenclature system, the IUPAC, the old papers, they call it Geneva, and the Hill system for helping searches. And plus the indexing systems like Beilstein that I don't know anything about, that's kind of before my time. But these things are very hard to learn. You're talking about, I see, 1.5, one place, 3 years of learning how to do the indexing. So in 1946, a lot of stuff I want to talk about is from 1940s. 1946, Dyson proposed an improved notation system, still based on the IUPAC of looking at the longest carbon chain and building on that. That was more useful, easier to use, usable by punch card machines, and a few other traits. And so you can see here's an example of the Dyson notation. It's the C3 is there's 3 carbons, and then there's the oxygen attached to the second position. And the bottom was a bit more complex with the benzene there, coming up to nitrogen with the, you can read all that later on. It's pretty cool stuff, but yeah, don't need to know it now. So Dyson listed in the 40s the goals of what you need in these sorts of line notations. And let's see, simplicity of usage, I mentioned. And then number 7 there is ease of transfer to punch cards. So doing things like being able to compute a molecular formula just from the notation. Being able to make indices, new stuff with punch cards. He proposed this, he gave a talk. The people, the Gordon Kelly and Davison people here, they saw the talk and went, this is great, we'll do our own. Dyson convinced IUPAC they need to look at this. IUPAC started a commission on codification, notation, and punch cards. I made a call out to get people to submit their own notations. Dyson was president, so the call out says here, you can see 11 desirable characteristics. That's Dyson as president doing the same thing he was doing when he developed the Dyson notation. So in 51, they made a push out saying, here's the 4 ones that we're going to look at. The National Research Council did user testing and found out, well, it's a high error rate. And no one knew which one liked best. So they went back to the drawing boards and worked at it some more. Eventually, the Dyson became the tentative standard in 58 and finally finalized in 61. And almost nobody used it. A few people did. Dyson went over to chemical abstracts and they used it at chemical abstracts. And there's a few other people that did it, but almost everybody knows, if they know about the older notation before smiles, is Wiswesser line notation, WLNs. And there's this beautiful pictures that I got from Roger Sale, Nola Boyle, and Greg Landrum, and Roman Affentronger. Developed Open Babel supports a subset of WLN as input. Sure, why not? And then there's really gorgeous pictures so you can see how the mapping is between what WLN looks like and what smiles looks like. So it starts off with T56 is the 5-6 ring on the bottom left and builds up afterwards. Now, WLN had some great advantages over the other systems. One is it was based on functional groups, not carbon chains. So you could start doing things by searching directly on the fragment code, or on the notation, by looking at it as a sort of fragment code, instead of having to put into a machine or manually search in some sort of other indexing system. It could also be used to make printed indices. So this 1960s, you're not going to dial up even back then to do a search. A few people did, but it's very expensive. So you could do, say, publish your WLN, but shifting every different group over so that you can sort all different possibilities and then print that out. So you can search it by just looking up an alphabetized list. The thing that amazes me about reading these things is you see generating 55,000 line notations would cost about $10,000 then, or about $85,000 now. So no wonder they're doing all this research back then. This is really expensive stuff that they're trying to make cheaper and make cheaper. I have citations for this, but okay. So, but by the time I entered Cheminformatics in the late 90s, I only heard of WLN every once in a while. It kind of died out in the mid 80s. And there's a couple of different reasons. You look back and there are reasons for why you have these notations. So you can make molecular formula, or you can calculate the molecular formula without having to go through making the line notation. But Garfield showed in the 60s, his PhD thesis was you could take the string and actually make an algorithm to understand the symbols inside of the notation. Graphical inputs started to happen. Canonicalization happened in the 60s as well. So now you didn't have to do some sort of elaborate formula, elaborate set of steps to be able to give a unique name. You could just put it into the algorithm. So by 82, there's a special JKX publication, WLN. Lots of people saying, like Wiswesser, they're saying next 20 years of WLN. But you also see that programs are shifting to moving WLN as input, but internally they're using connection tables. So connection tables, what are those? Those are something that was developed for doing substructure search. And I've been able to find probably a blog about this in the next, well, at some point. I'm able to track it back to 1947. And here's a letter from Calvin Moore's, here's a letter from Charles Bernier from Chemical Abstracts to Calvin Moore's. He's at Chemical Abstracts saying that there's a growing demand for searching about groups that aren't indexed, because those sorts of searches right then take months to do for an indexer. And what happened is Moore's, by the way, this is in Boston, so the connection table came out of Boston. He came up with this organic group selection mechanism and then fleshed out a bit and described more about it in a 51 publication. So I think this is the earliest connection table publication. And you can look at it and go, okay, well, that makes sense. It's a bit inverted. There's an atom type to atom indices, or index numbers. And there's a different table for single, double, and aromatic bonds, but that's fine. He points out it's only usable by computers. And at this point, there are no commercial computers you can buy. It happens to be that Moore's had been one of the developers of one of the early attempts at computers. So he knew probably more than most people, almost everybody, about what computers could do. And he described that you could do substructure search using this. Here's his algorithm. It can be programmed in a UNIVAC or other computing machine. So it's a bit optimistic, but the basics are there. It wasn't until 1956, it was published in 57, but it's done in 56, when an undergraduate intern, Louis Ray, and Russ Kirsch, on this machine that you see there in the picture, did the first substructure search. This machine, the SEAC, is probably best known because it's the first digital image on that corner there, and that was Russell Kirsch's son. So the first digital image was the same person who did the first chemical substructure search. I should say the first atomic level search. DuPont had a really cool system beforehand. Basically, throw money at the problem, and you can make a really cool system. The only thing I point out here is that they didn't actually have bonds. So they had connections, but the bond type, double bond type, was its own element. So that's a bit unusual. Save space. And what's nice about this paper compared to some of the DuPont work earlier is it gives you a framework for how to think about, you do screens and then you do the substructure search, because substructure search is very expensive. How expensive is it? There's a really cool story. There's a video, you see it down there on the bottom. It's the H-bomb project. Well, that's what they said. So what happened was they had this machine and they're working for the government, so they go around, who needs computer searches? Who needs computer programs? And the patent office says, well, we need some way to find chemical structures. And so that's what they worked on. But the algorithm was so ponderous, so slow, that we decided, I hope we don't have to use our program in the patent office. Well, in those days, a tool you hoped you wouldn't have to use was the hydrogen bomb. So we decided to call our program the H-bomb code. When the coding sheets got misplaced, the FBI came in. I love that story. So the next about 20 years were spent on trying to develop good screens, because these substructure searches are horrendously expensive. Even the screens themselves are expensive. So you see here the paper from DuPont, which I already said had a huge amount of money. They're still thinking, how do we save the money by developing good screens? Now what I like is these screens are a continuation of the punch card code techniques that were developed in the 40s. But even screens at this point are expensive. So Grimace, which is the German project, started in the late 40s. According to the link down there, it was costing 2,000 Deutschmarks to do a search. And as best I can tell right now, that's $4,000 to do a substructure screening search, not a substructure atom matching search, but just the screening part of it. So their solution was, he went over to the US, met with the father of basically the connection table, Calvin Moores, and learned about a technique of his called Zato coding, which he went back, implemented, and it cut the cost by a factor of 200 by taking this big long fragmentation code and making it more condensed. So what is Zato coding? Another Boston area invention. His master's thesis at MIT. The idea is, if you think of every descriptor you have, it has a set of codes. So the chemical descriptor, say 2 cycles in this case, he's not a chemist, might be mapped to, in this case, 4 codes, and the descriptor, let's see, CO in a 5 cycle, connected to 2 codes. The number of codes is based on the information content. And you see there on the right-hand side, there's the card. It's a notch card, so the 2 holes in the top, 2 holes in the card, and then use that in your system. Moores is not only Moores is working on a chemical indexing system for Merck Sharp and Dome. So he already has some experience, and this is deployed. He's the one that not only came up with the term descriptor, but he's the one who came up with the term chemical descriptor. So I said connection tables are Boston, chemical descriptors are also Boston. Now in 1957, that was the first publication of the substructure search. Also in that year was Sputnik. And Sputnik, well, it shocked a lot of people. How did the Soviets do it? And one of the things that, according to Michael Lynch here, was that the information was out there, but it wasn't indexed and available enough for people to understand that the Soviets were going to do this. And suddenly after Sputnik, funding for information science and technology research became readily available on both sides of the Atlantic. And you start looking at the projects, and there's just like project after project after project start. Now the money is available and the computers are getting cheaper. So people can start doing stuff. Medlars is not chemistry. It's the predecessor of Medline. Medline is Medlars Online. And somehow or other, I came across the video 5 years ago, and there's nowhere online. It shows you what it looks like to do a computer search in the 60s. You have other projects, chemical abstracts, got hard to track this number down, at least $3 million, then time $32 million now to do the computerization of their system. The Army had a project called SIDS that I really want to investigate more, and more projects in Germany, in France, so many different things. And people now had a chance to explore. So you can think of substructure search as something you couldn't do with a punch card system. Here's other things you couldn't do. Dendrol was the first, it was AI of that time. It was the first AI program to look at, let's find algorithms to try to find matching for, I think it was spectroscopy data. Mass spectroscopy data. And I love this one, a paper from 1965. It's a circular fingerprint. They're called penny codes, and they're influential because I see like Michael Levitt's thesis, PhD thesis is talking about penny codes in the 70s. And you look at that and go, yep, that's penny codes, and there's a canonical penny code. And I love the phrase that I love this quote in the bottom. The ultimate rapidity of search will be a function of the ingenuity of the computer programmer and poses an interesting application for an experienced bit juggler. I have a software product that searches like the RDKit generated circular fingerprints, and it does a lot of bit juggling. So I just love that quote. Now we enter the point in the 70s and the 80s where I don't know so much. I just want to point about that in the late 70s is when MDL started to sell their Mac system. And it was a graphical entry registry system for your entire corporate data set. Basically, now you could buy a computer, buy a program, make it go. Probably more than that, but compared to previously when you had to build your own computer or write your own software, it was much easier. Now you notice MAX in the bottom, the MAX molecular access system. That is the same MAX as when you talk about MAX keys. The MAX keys were developed as substructure keys for the MAX system. They're not designed for similarity. In fact, if you start reading through the literature, you wonder, they're not talking about similarity. Where's similarity? Something that's so intrinsic to cheminformatics now didn't really exist in the literature until the late 1980s. The concept has been around, of course, for a long time. I've tracked the legal, the patent office says in 1970, expectation that compounds which are very similar in structure have similar properties, but there's no way to make that, I guess, mechanize that. So in the 1960s, they had maybe maximum common substructure. There's some very early work in 73, 75 of looking at bit strings, which are based on they're augmented atoms, so they're kind of like radius 1 or so circular fingerprints. And Randick in the chemometrics area is starting to look at this too. It wasn't until 1986 when Tanimoto became popular. So basically the people at Sheffield started looking back at some of the work that was done earlier, a decade earlier, analyze it compared to other systems. Okay, it looks like Tanimoto is good. And then they implemented nearest neighbor search for the Socrates system. Again, this is the 1,315 substructure screens because they're already available. Do the search, find out Tanimoto coefficient is pretty good. And from what I understand from Peter Willett, almost immediately other groups said, we can do this. And it's the sort of thing of Friday afternoon, get it done. Wow, this is amazing. And what screens are at hand? They've all got the MAX system, the MAX keys are at hand. So anybody who's using MAX keys now, they aren't designed for similarity. They're designed for substructure search on computer systems in the 1980s. And it's just like, wow, look at that legacy. So the MAX fingerprint similarity, the Tanimoto similarity, is only one of many different threads of similarity that was developing in the 1980s. And so in the 1990 book, Johnson and Magyar, they had worked with a bunch of people to kind of have a book that gives you an overview of what's going on and the state of art is for molecular similarity. So if we talk about cheminformatics, I think that's a key difference between the modern cheminformatics and what happened before then. But even if you look at that, there's a few things that are missing. The term fingerprint doesn't exist in literature until the early 1990s. Everyone's talking about things like keys and screen set. Daylight fingerprints are probably the most novel technique that Daylight introduced to cheminformatics. And so those who don't know it, the basic idea is you take the structure, you do a linear path of up to a certain length. In this case, it's going to be oxygen, double bond nitrogen, and so on. Use the atom and bond properties to make a number based on the hash algorithm. Use that as a seed to random number generator and get 1, 2, 3. It depends on the actual length. Daylight never documents this. you have to talk to old-time Dalke people to figure out that they had a variable length fingerprint, and it's not in the literature. Anyway, so and then you look at this and think about this, and that's a random superimposed code. That's the same thing as Moore's was doing back and forth. No, it's not. Sorry, it's not the same thing. It's enumeration based. Moore's was you have the descriptors, you come up with a table. If you have a new descriptor, then you add it. This was an algorithmic way to do it. And I've also I've asked Dave Weininger about the connection. He had no idea what was going on, but I've learned from other people that, yeah, it's another story. This is a story about history, not about cute little stories. So another thing about daylight is they kind of reintroduced line notations to cheminformatics. So Dave Weininger tells a story about how SMILE started in some sense because of Nixon. There was a start of the EPA. So the EPA needed to track chemical compounds, pollutants that are in the water. So they needed a way to input chemical information. And they don't have chemists with a couple of years of knowledge. They had clerks. So he developed a very simple system, very simple compared to almost every other system beforehand. And if you look at it, compare the Dyson Desiderata, it throws away almost everything. It's emphasis, if you, of those original Desiderata from the 1940s, simplicity of usage, easy to program into a computer, and because now we have the Morgan algorithm, uniqueness. It did take Daylight a few more years to figure out chirality. That was another problem with the WLNs and Dyson, was they could never handle chirality or tautomerism. So let me go back to the only thing that looks like SMILE's precursors that I found in the literature was in the same issue of the Journal of Chemical Documentation, 64, two publications. The first one is very SMILES-like, just a different way of writing it. And the second one is a Polish type notation for chemical structures. So a few years ago when I was talking with Noah Boyle, he was talking about the deep SMILES idea. And I was pointing out, well, it's this paper back in 64, and that's then helps explain my contribution to that project is making this connection to the old literature. One last major thing about the daylight is it's great to introduce a new notation. But if you look at the literature, there's notations, there are notations. For a while, it seemed like every issue was coming out with new notations. And fingerprints, those are pretty clever. I mean, like I said, there's nothing like them except for this connection to the same ideas of information theory that Moore's did back in the 40s. But I've called Weininger's realization. I have a blog post about it from a few years ago, which is if you look at chemical data, it doubles every, at least back then, I don't know what it is now, every 10 to 12 years. But the price of RAM is decreasing. RAM prices in 85 were $400. It's order of magnitude more for RAM than for disk, and even then it's pretty expensive. So you're going to keep all your information on disk to try to lower that overall cost. At some point, RAM prices go down. I guess it's this way. RAM prices meet up, so you can finally keep all your data in memory. And it's hard to find this information, but if you look through the literature, you can find, looks like at Chemical Abstracts, it took them about 330 bytes per record. And look at the daily stuff, it takes about 1/3 that amount of space per record. So that means that they could fit in your entire corporate data set in memory and do searches at something like 1,000 times faster because it doesn't have to go to disk for everything. And people will pay for that. And people will switch to using a new notation. And people will use your fingerprint system because it's so much better at doing the stuff that they want to do. In the 1990s, reaching the end of the talk here, 1990s happened. I want to say daylight is the last of the chemical information systems. I mean, sure, you can have more systems, but I want to demark this as before then, if you wanted to do a chemical information system, you would do it all yourself. Daylight developed their own databases from scratch, did all the testing you need to do to have a database that your data doesn't disappear if the program crashes and things like that. By the 1990s, you start having databases that are extensible, so you can add new data type in. Informatics Database, Oracle cartridges, Postgres, all these databases now have a way to add chemical stuff to the database, so you're no longer going to be a complete, I provide a chemical information system, it's going to be I provide a plug-in to your corporate system. And even Daylight started doing this late 90s, they had the Oracle cartridge, and their user base, which had been all these geek chemists that were writing software for the corporate system, we're moving to, we are IT or maintain a database for a system that happens to use Daylight to do the registration. in addition, the thing I said about Weinberger's realization, RAM keeps on getting cheaper. So now anybody can have all the RAM on one machine, load, say, all your corporate fingerprints in your computer, and do things like maybe spend a few weeks and cluster everything. Nowadays, of course, it's 20 minutes or so. But it's just like, so you look in the 1990s and you start seeing all this thing happen because you have similarity and you have the ability to process the entire data sets you have on regular computers. And you're starting being able to do predictions, and that's what leads us into modeling. So that's why I think that just the cheminformatics, as we think of it now, requires this input from the 1980s concept of similarity into modeling to make it be cheminformatics as compared to what happened before. But the thing I think is most amazing is a few things. One is these are the same techniques they were using in the 40s in many cases to do prediction. You go back to these people in the 40s and you say, I do this and this. Like, okay, we get descriptors and that, oh, similarity, that's pretty interesting. The other thing is the other way around. So I think of substructure search as hard to implement. It's a lot of graph theory. But then the people that basically anybody who thinks about the problem back then kind of knows you want to do it this way. They could have been doing similarity search on punch card machines in the 1940s. They had all the technology. The early computer systems all had that same technology, but it took another 40 years before we finally figured out we can mechanize the concept of similarity. So that's one of the things I enjoy about doing the history is to figure out why is it, what is going on here? What's creative? What's not creative? What's hard? What's easy? And last bit here is, of course, in the 1990s was the World Wide Web starts happen. It's building on the dreams of hypertext systems like Project Xanadu in the 60s, which is built on mimics other similar projects in the ideas in the 40s, which is built on the Mundanium going back to the 1890s, which is built on so many dreams in between now and then. So if you want more history, especially if you want history about the 70s and 80s, which so much of it, then it's not in the literature because it's all more corporate stuff. You go see the Chin paper from 2006. And a more academic-oriented view is from Peter Willett, and nice little timeline at the bottom. So I'll leave with a bit of advertising. If you want a high-performance fingerprint summary search tool, anywhere used Python, written by an experienced bit juggler, try ChemFP. It's available from there, or I'm also available for consulting in software development. And now I'll take any questions.
Oh, thank you, Andrew. I'm always astounded by the amount of detail I don't know about my field. This is
well, if you spend 5-6 months at it, this is a lot of digging through old literature, and in some cases, going to the archive where Moore's papers are to dig up what was going on, and then coming across publications from the SIDS project in the 60s. And went, wow, they were doing that, and then, but they weren't using the term connection table in 64, but they were okay, and then all sorts of things that really require, yeah, that nobody's going to pay for. So if somebody wants to buy ChemFP,
well,
it will help fund my
I will say
research.
MFP makes me look good every day, so it's well worth it.
Okay,
There's
so
a couple of questions that are coming in. Alex is asking about the Freer dataset. It seems like an incredible resource. Is it digitally available, or is it only?
well, it's scanned. It's totally scanned, but other than that, let's see if I have. I should have Freer. Yeah, if you go to my slide on Freer code, on the bottom it says Donald E.H. Freer, a catalog of insecticides, and it gives you an archive.org link. You just click on that and you got yourself the catalog. However, you have to transcribe it all by hand.
Okay, I'll be sending out actually the link to Andrew's talk at the end of probably later today. So some more questions I'm not sure I quite understand Adam's question, but this cheminformatics system must have seemed ripe for automated exploration. Did anyone try writing a simulation exploring these elements?
I don't know what that means.
Yeah, if you could explain further, Adam, that'd be wonderful. And we have a question about selfies. What do you think about selfies?
I'm sorry, I'm in the 1940s through 1960s. Ask me about different types of edge notch systems, and yeah, no, I don't have an opinion on that.
Okay, so Unfortunately, this is
Okay, so here's what happened: is that the deep AI is going on right now, and I haven't been following it because I've been doing this very classical cheminformatics, fingerprints, notations, and trying to understand this better, because I actually don't think enough of it's documented. This concept of how do you develop a substructure screen? None of the literature talks about it. You look at the cheminformatics textbooks, the cheminformatics handbook, none of them talk about it. There's papers you have to read, like there's a one from 1974, 25 or so, a paper I adore that's using the same Zeta coding system to try to make compact screens. But it's not, reference is not important anymore. And so this is more of where my interest is. It's very classical cheminformatics work.
so from a chemistry perspective, a question I have is, what are we missing? So you look at NBL docs, and there's dative bonds, and there's metal coordination and things like that, and that gets harder and harder because we're dealing with a model.
So if I go back to my concept, one of the things I said for this talk is we're missing people to pay for this. Because you look back at these 1960s things, and they're spending tens of thousands of 20,000, hundreds of millions of dollars to do things that you would do now to say, oh, we can do this. If people really wanted to handle all these things like what do you call it, bonds that have multi-atoms and stuff like that, those ideas have been around, but there's no one paying for it. So we're looking for somebody who wants to pay for it. Really, that's what it is.
Okay, so this is a little follow-up from Adam. He meant that an automated way to describe chemicals seems to allow descriptions for ones that have never been formed. So he's thinking about a ML or some other algorithm that explores those rules to make interesting new stuff.
So that's entire, I mean, Dendril starts doing that. It just enumerates all possible substructures, and I've got ways to enumerate, and there's also ways to enumerate. The question is how you do the direction. You explode pretty quickly, and you all know better than I do what's going on now with deep learning, and there's the genetic algorithms, and there's been so much on this that this is an entire, it's a topic that first I don't know about, and second would probably be another 3 hours just to cover it all.
It would. I mean, in my experience, it tends to exploit the model very, very quickly.
Okay, that's what AI systems do.
So Brian Cole has a question about, since we're dealing with much larger systems with enumeration now, is there anything clever we've forgotten about to help?
I really love Zeta coding. In the modern sense, you would think of it as, what is it called? The bit screen, the fast rejection thing that was so popular 10 years ago in Google circles and stuff. The idea of having a variable bit length to depend on the information content of your query is something that seems to be missing from a lot of work. But I would say also in general in cheminformatics, I talked to you about this a couple years ago at the, last year, the Arctic meetings, I think we haven't done enough with the constraints systems.
Yeah, we tried the constraint system. I think Brian Cole did that too. And it was, if you set up the problem, it actually is really, really amazing. Mm-hmm. But that's another talk, of course. Not sure we have, if anyone has another question, that would be follow on, but do you, Andrew?
Well, I could say I don't have it handy, but if you would just wait just a moment. So a few years ago at the Sheffield conference, I made some. And so you can see these are, you cannot, back in those days, you could go down to your corner printer and be able to do specialized printing nowadays. I had to get one of those robot cutters that does things for you. There are programs, I'm using 21st century technology to make 1940s technology. But you can see here, here's what these things might look like. Let's see if it comes out well enough. Got holes on the top that are supposed to be for substructure filtering, and indices and molecular weight in here. And should be able, I can't do it anymore because I don't have the index anywhere. But you can do things like stick in the needle, poke it through, and the usual problem is you have to organize these things first. And then you pull out, whatever bit I happen to randomly select. I've selected those cards, and those have come out. So I had some kind of experimental archaeology 5 or so years ago doing this.
So how many cards do you need before it gets faster than a computer?
I'll have you know, people were using this until the early 80s. I have talked to people. Who was it? Jack Delaney, who's now at OpenEye. And when he started at Kodak, people were still using this for their private collections in-house. But for you've got your own personal collection of compounds. Okay, sort it, pull it out. They're called key sort cards. They were used in the whole Earth catalog in the 70s or so. There was until microcomputers happened that finally people could have their own personal computers to do these searches. They were still in use.
Well, speaking of which, of hidden documentation, I also had a conversation with Jack Delaney back in the day, and he informed me that the daylight paths were not all linear. They had subgraphs.
Yeah, I've heard that too.
Coded ones.
Mm-hmm. For those watching daylight, consider themselves, they're kind of outsiders to cheminformatics. I think it's too bad, but that's the way it is. And they were also a company and they kept some things proprietary, so they always had the advantage.
Well, Andrew, again, thanks for the talk. It's recorded now. You can show it to your kids when they're interested. But
Okay.
Everyone, virtual clap for Andrew, and this is awesome. Thank you so much.
Thank you. Thank you for listening.
Bye, everyone. See you next time.